Okay, the record is now on. So let us start. Okay. I didn't do this example before the midterm exam. So because I thought it was non-science way, we didn't have anything to do with that. But I also, what I realized later on was that I missed the opportunity to show you how to handle the cantilever stuff. But I think you guys are okay. Judging from the homework, it should not prevent you to learn how to do it. Okay. So what we need to understand from this situation, I'm just going to go over it very quickly, okay, because it's not difficult. This, we have the lateral restraint. To prevent side sway. So we can safely say that the moment that occurs in this structure will be due to the load and the joint rotation. And we can proceed to use a moment distribution to solve this structure right away. Okay. So no moment due to side sway. Say we can proceed as usual, because you should realize by now that moment distribution is the method that was built to solve the indeterminate beams by introducing the mathematical approach to help solve the slope deflection equations. So if we know that there's nothing to do with side sway, we can just proceed and fix this. Okay, and you just go ahead and calculate the relative stiffness and so to get the distribution factor. So if I say this is A, B, C, and D, my KAB is CI over 6. My KBC is 3I over 6. And my KBD, so let's move this up a little bit. My KBD is now 2I over 6. But this cantilever stuff, some of you have already known that I can sort of change this into constant moment, right? 25 multiplied by 3 gives me the moment. So in fact, this can be rewritten in this form with just moment. So that means D is also a simple n, and therefore I can modify it with the factor of 0.25. Okay, so that becomes 3/4. So that becomes I over 3. Oh, geez. Excuse me. Just a moment, guys. Important. Okay, so once we know this, we can proceed as usual. But just this time, joint B has more than 2 members. That's all. Okay. So from this, I can use K equal to I over 6. So this becomes K. This becomes 3K, and this becomes a 1.5K. Okay. So now I can just write this down. So the distribution factor from this, the total at the joint will be 5.5. We have 1, we have 3, we have 1.5. And you can do the distribution factor by yourself. Let me just try to finish this quickly. That's 0.18. that's 0.27, and that's we're gonna have to use you know, art of positioning, maybe 0.55 here. Okay, and we only have one fixed moment from this uniform load, which is 9. So this is -9. This is +9. But we also have the moment due to this. Okay, and the resisting moment should be in this direction, and therefore it becomes negative of -7.5. Okay, and let me move this down a little bit. Okay, all right. So we balance that. This becomes a you can see that this is minus 1.5, right? Oh, sorry, it's plus 1.5. Bad morning against me now. So we need minus 1.5 here. So then that's it for this. Okay. And you see, because I have modified it as a simple end, so it ends very quickly. And this will be carried over to this by half. So it's minus 0.75. Okay. And now minus 0.75 will be resisted by 3 members instead of 2. And we have 0.18. And we did plus 0.75, right? Multiply by, oh, and we also have minus 9. So we need to resist minus 9.75. So right here will be 0.94. Here is 1.42. And here is, oh, we have another load here. Sorry, I missed that completely. My bad. So we have a fixed moment here as well. 4.5, that's from point load, and minus 4.5. Okay, and now we are resisting this, the total of minus 9.75. So here we have another, oh, I'm sorry, it's not minus 0.975. The total is this one. My apologies. Correct, that's the total moment. So it is about minus 5.25, I suppose. Yeah, so multiply with 0.55, so we have another 2.89. Okay, and then because the two other ends are fixed, so it would be a good idea to try to transfer something over there all the time, if you can. Okay, and that's 1.45. And that's 0.47. But then that's it. Okay, that's the end of the process. I don't want to go through deep details about this one because it's just like before. The focus today should be on the sideway subject. All right. So this is just to show that if the moment I'm sorry, if the frame does not sway. Okay. If the frame does not sway, you can go ahead and use moment distribution to solve the structure. So I can safely say that the moment we have now, okay, this is the end of the process. The moment that we have now is the moment due to everything that is, you know, in the non-sideway category. Or I can say this is the moment due to the load. Okay. Now, when the frame is going to sway, we will again have the moment due to the load like this, but we will have to go one extra step to try to determine the moment that caused by the sway of the structure. Because let's say if I have a structure like this, okay. and I put the load like that. Okay. Let's say if this is non-sideway, it means that we need to have the lateral restraint somewhere, correct? So let's say if I try to apply the lateral restraint like this, your frame does not sway, correct? And because you don't have the load on any member, you just have the load on the joint. So this structure will duly have no moment, because if you have the support there or the restraint there, this one will take care of the load. And the structure has zero moment. You agree to this? Everyone? Oh, please. In total in the class, we have only 7. At least the least you can do is talk to me, you know, just the 7 of us now, you know. And
could you repeat the question again?
Repeat the question. Okay. I don't remember.
Okay, let's go on.
Let's try. Okay.
Yeah.
Let's say if I remove this first, you know that this frame is going to sway, correct? This frame,
yes, of course,
is going to sway, and therefore it is going to deform.
Yes.
There will be moment.
Yeah.
Even though there is no load on the member.
Mhm.
Now, if I apply the restraint and trying to stop this frame from moving by adding the lateral restraint there, now you are, because there is no load on the member, your structure will have no moment at all, correct? Because this restraint takes care of everything.
Yes.
Because this reaction will have to be equal to that force. And so the frame will remain intact. No deformation, no nothing. Okay. Now come to the frame for this. This one, we have the external load here. We don't have the sideway because we have lateral restraint in the lateral support here. So, but we still have moment due to the load, which we can solve, right? So if we have the external load, we don't have sideway, we still have moment due to the load. Now let's move to this. If we don't have the load and we don't have sideway, it means we don't have moment at all. Because this is the load, yes, but it is applied at the joint. So there's no load on the moment, so no moment. Okay. So, but now if I remove this, oh, sorry, technical glitch. If I remove this, now your frame, why is this? Yeah, whatever. Seems out of place a little bit. If I remove the restraint, your frame will sway, and you should think that it will have moment, correct? Do you agree that it should have moment because it will deform, right? And when your structure deforms, it means that there must be internal moment. Many students still cannot sketch the deflected shape. If it deforms, it must have moment. Simple as that. So we must find a way to calculate moment due to side sway. Okay. Okay. So now, when you are dealing with the side sway moment in slope deflection, you have the term, correct? Correct. We have the formula for friction moment. It's 6 EI delta L over L squared, something like that. So if you can recall, FEM due to side sway in SD it has some form of the delta in it. I don't remember exactly, so don't take my word for it, but I think it looks something like this. So you'll see that it has this delta term in it. In other words, if you know what delta is, you should be able to solve for fixed moment in slope deflection, right? But when you don't know, it's part of your equation, then you can solve it with an extra equation. Now, for moment distribution, we always begin the process by calculating the fixed moment. And when fixed moment comes from this displacement, how are we going to put the fixed moment into our process for moment distribution? Because this becomes the unknown, and the formula for fixed moment due to side sway is in the form of deflection of displacement or lateral displacement itself. So in other words, there is no way we can calculate fixed moment due to that. What does it mean? We are going to have to assume some numbers. Okay, because we don't know. It's impossible for us to determine the delta beforehand because it's part of the unknown. And we need to have the fixed moment in order to carry out the moment distribution. And because we don't know this, we can't calculate fixed moment directly. We're going to have to assume something. Okay, so that's the idea. We're going to have to assume something. So let me try to give you the basic idea of this first. For the moment distribution of a side waveframe. Now I am talking about the case when we have, say, this case that you're looking at, we don't have the moment due to the load on the member, correct? So we can start off by guessing this right away. But let's say, what if we have the case where we have the load on the member as well? What do we do? So let's look at the, say, ideology or concept of this. Okay, let's say if I have this frame, it doesn't matter what number I have. Okay, and then I have a load like this, not in the middle. Now, because this load is not symmetric, so it's going to push the frame to the side, even though you don't have lateral load, but this structure will have side sway, correct? Because of the unsymmetric loading condition. So if you have a case like this, now you know you're going to have both moment due to the external load and then moment due to side sway as well, because the unsymmetric loading condition will push the frame to have the lateral displacement, and therefore you have it. So it's safe to say that this frame will have first moment due to the external load itself. A second is moment due to lateral displacement or delta. The two cases now. Okay, so the first step number one, we are going to prevent the side sway. By adding the support like that. Okay, or doesn't matter, you can add a hinge. or roller. But let's say, because I usually draw a hinge, let's draw a hinge. Okay. Now, if I provide the lateral restraint like this to the frame, now this frame becomes similar to this frame, correct? Because it has lateral restraint. So you can proceed and perform the moment distribution to obtain the moment like this. Okay, so I'm just going to skip that and let's give you some number. Let's say this load is 20, maybe 20K. We perform the moment distribution process just like the previous example and end up with some number. Okay, because I took this from the textbook long time ago. So let's say prevent sideway and carry out moment distribution. After you carry it out, you're going to have the end moments as usual, correct? So these numbers are obtained when you finish the process. 23.5 minus 23.5, yeah, 12.7 minus 12.7 minus 6.3. Okay. Are you a little bit confused by this? Now, because we fixed this frame with the orange support, this frame becomes a non-sideway frame, which means you can proceed and carry out moment distribution to obtain end moments as usual, just like the previous example that we did like 20 minutes ago, 10 minutes ago. Okay, and once you have these numbers, you can proceed to also calculate the shear and the stuff. Okay, so like this, for example, you have the end moment, right? You have the 23.5, you have 11.8. So you can now calculate your reaction or base shear as before. And this is 1.77. Okay, another, this time it is the counterclockwise both. It's 12.7, 6.3. This guy is going in this direction, 0.95. Okay, just look at this. You see, if we don't have this lateral restraint here, if we don't have anything here, you just look at the reactions you have. Remember that this frame does not have any force in X direction at all. So in the normal world, the summation of these two reactions should give you 0, right? But then it doesn't. So that means the difference between these two reactions, as you see, becomes the reaction here. That is 0.82. Are you still with me?
Yes, yes.
Good. Okay. So this, when we look at this imaginary lateral restraint here, we know that it has to provide us with the reaction equal to 0.82 to stop sideway. But the thing is that this lateral restraint does not exist. So in fact, when I remove this restraint, this frame is going to move to the side. Correct? Which means it is as if this frame is being pushed by this imaginary load. Okay, this load is not true. It's just in a, it's like maybe alternate universe, some sort. But this frame, as a result of the unsymmetric loading condition, it was being pushed by this unseen lateral force. So to complete our free body diagram and equilibrium and stuff, we need to proceed and try to find the moment caused by this lateral load. Okay? Any question? Step number 2. I'm trying to draw the equal frame. Okay. How should I name this? Step 2. We are going to assume moment due to side sway. Okay. Now we have to make assumption, but we have to make the correct one. So let's say, because we got a little bit information from the first step that this frame is perhaps being pushed by this. So I think I'm going to assume that this frame will have displacement to the right equal to delta. Okay, that's what I'm going to assume. Based on this information, now I believe that we all should know that this delta should be equal, correct? Now say example. Let's give it some name, okay? A, B, that's my B, ridiculous. A, B, C, D. Let's assume MAB equal to, because this frame is moving in the clockwise direction, you can see that, right? The frame is moving because we assume the movement in the clockwise direction. So it's safe to say, we can assume this resisting moment to be in counterclockwise direction. So let's say I am going to assume MAB equal to -30. It can be any number. I'm going to assume -30, okay? So what then happens, the next is this. If you assume this -30, based on this number, you should have other n moments with the numbers according to this as well. So let's say we assume this equal to -30, right? This is the assumed number. Okay, so what else do we know? Let's say if I assume this to be minus 30. Okay, I know that member AB is of the same member, and when it moves to the side, the end moment that resists the side sway should be equal to MAB, right? So by assuming this, I also know that this has to be minus 30 as well. See, I use different color now. The blue color is the one that I assume. Now this is the ensuing number in accordance with this minus 30 that I assume. If I assume this minus 30, this has to be equal and go in the same direction. Correct? Because we know it goes like that. So if you assume this to be minus 30, this better be minus 30 as well, because these two end moments should help resist the lateral movement. Are you still with me?
Yes, yes.
Good. So now from this is member AB, okay? Now we know another thing from our structural knowledge is that we know that if this is delta, that is also delta, providing that EI are equal for AB and CD, right? And lengths are equal. So if I know this is delta, that must be delta. That means for member CD, because they move with the same lateral direction, it has to be the same moment that trying to resist as well, correct? So by assuming this to be minus 30, you must assume this to be minus 30, this to be minus 30, and this to be minus 30 as well. Let's say if I assume this number to be minus 100, minus 100, these three numbers have to be minus 100 as well, because we know the relationship. We can assume these three numbers based on the relationship of the members that we know. Are you still with me?
Yes, yes.
Okay. Let's say if you assume this 30, you cannot assume this to be 60. Or you cannot assume member BC to have end moment, because member BC does not sway. It stays flat. It has rotation, but it does not sway. The joint remains at the same elevation. Okay, so now we have end moments. The other end moments are assumed accordingly. Okay, now of course that means we are going to have to do another distribution procedure. But begin with end moments equal to minus 30, minus 30, minus 30, and minus 30. And of course, you again carry out our moment distribution, and then the final number, when you have the equilibrium, it is going to be, the final number is minus 20, 4.4 minus 19.4, just numbers, 19.4, 20 minus 24.4 minus 19.4 has to be equal like this, right? Because it's size way alone, 19.4. Again, now from this, you can use the free body diagram to calculate the shear again, correct? What color did I use? Okay. Now the free body diagram is minus counterclockwise. You can use this free body diagram to calculate base shear again. And because the two columns are identical now, your shear is going to be like this. Same. And yeah, the shear now is 2.19. Another one is also 2.19, correct? So the summation here is 4.38. Okay? So now the end moments here, are the results of the frame being pushed by 4.38. Maybe is it tons? Did I use tons? Actually, it's a pound-foot unit, so I don't want to talk about it. Okay. Okay. Or this. Okay. Now you have this number. You see, you have this number. These are end moments, but these are the numbers based on the frame being pushed by this load. Now, what we have from step number 1 is we know that the imaginary load that pushes the beam is 0.82. We assume number, say minus 30, but we end up with, it's like a back calculation. We end up with the load that is 4.38. We want the moment caused by the load equal to 0.82 K. But now we have the moment here caused by the load equal to 4.38 instead. Okay. Oops. Instead of 0.82 that we want. So let's say if you have magic and you assume some number and then in the end you get 0.82 here, you are done, right? But no, you don't. It's not going to happen. So now, moment caused by 0.82 is what is needed. Instead, the assumption gives moment due to 4.38. So what do we do? Luckily, we are in the elastic world, so the moment caused by the load is proportionate. That means we can use the linear relationship to turn the moment caused by 4.38 here into the moment caused by 0.82 by simply using the linear relationship. Okay? Luckily, linear relationship. Oh, sorry. Relationship can be used to calculate moment caused by 0.82. So now I'm just going to bring this. What do we have here? Running out of time. So it's like we have 19.4, that's that kind of thing. Okay. Minus 19.4, 19.4, 19.4, minus 19.4, and minus 24.4. My handwriting is pretty awful. You okay with that? Okay. We multiply this whole thing. We want the moment due to 0.82, but we have moment due to 4.38. So we have to multiply this by 0.82 over 4.38. Now we're going to have moment due to 0.82 because it's linear. Okay. And let me finish this before the break. So that's step number 3. Combine them. Okay, now we have we're going to have the moment due to 0.82 now. Okay, it's going to be, I try to write better, minus 4.56 minus 3.63, 3.63, oh, 3.63 minus 3, oh, minus 4.56. Okay, now you should know this is moment due to 0.82 lateral load. Okay, plus moment due to your external load on the member, which we have finished long time ago, which is equal to 11.8, 23.5 minus 23.5, 12.7 minus 12.7, and then minus 6.3. This is the moment due to external load. You can say this is from step 1. Okay, so it's in a way superposition. You calculate moment due to the load, which is basically the here the non-sideway business, just like the first example that we did today, and then you go and figure out moment due to sideway, and then combine them by superposition. Right, so you say superposition works. Okay, so in the end, we have the answer. Uh, 7.2, 19.9 minus 19.9, 16.3 minus 16.3, and then minus 10.9. Okay. One extra step for the sideway problem. Again, it is pretty amazing how Professor Hardy-Cross could think about something like this. Okay, any question? Any question? Hello?
Excuse me.
Yeah.
Did you show for the calculation of the external load, moment due to external load?
No, I didn't. I just give you the final numbers.
Okay, of course.
Right here. Just to get the concept first. Oops, not this one. It's that.
Okay, I see.
Just see the concept, and you know the detailed calculation should be shown in the examples. So do you have any other questions besides that one? Hello? Any? I suppose that's a no. So let me stop the record first.